All right, so welcome to Chapter 2. We're going to take a look at water and aqueous solutions. We have a couple of learning goals that we're going to explore today. So we want to ask the question, what kind of interactions occur between molecules? And we're interested in learning why water is a good medium for life. And we want to know why nonpolar moieties, or why nonpolar molecules, are going to aggregate together in water. And then how dissolved molecules alter the properties of water. So we're going to take a look at a couple of those questions and try to expand and deepen our knowledge. So we're made of water. We intake water and lose water on a fairly regular basis. In fact, if you take a look at some of this information, you can actually see the total recommended water consumption in terms of ounces. And if you want to do a great exercise, convert that to liters just for dimensional analysis and unit conversion sake. And then you can actually look at total body water as a percentage of your body weight. And that actually is also a really interesting exercise to do, where you can use dimensional analysis to kind of unpack that, right? Figure out what that mass is in terms of grams, and then be able to use density to convert that again to liters. And you can kind of do that direct comparison. But again, when we're thinking about this, we know that water is the primary constituent of blood, cytoplasm. It's important in the lubrication of joints. It has a significant role in terms of heat exchange. It solvates other molecules. So we know that water is important. But if we put this at a very personal level and we think about water intake for ourselves, so it's recommended that, right, you drink minimum 1,200 milliliters per day. And you probably get about 1,000 milliliters from your food. And then when we oxidize the food that we eat, we get a little bit more. And so we have this rough total of 2,500 milliliters. And it probably won't surprise you to know that our water output through things like urine, skin, lungs, sweat, our feces equals about 2,500 milliliters per day. So one of the things that's a really interesting question to ask then is, well, what happens to that water that we take in? What do we do with it before we release it through our output? If we take a look at our total body water then, say you have a volume of 40 liters, which is 60% of body weight. And we partition that into our intracellular fluid, which is 40% of our body weight, so that's 25 liters. And then our interstitial fluid and plasma make up the extracellular fluid, which is the other 20% of our body weight, or 15 liters. And you can figure out, right, for extracellular fluid, the interstitial is about 80% of that, and for plasma, it's about 20% of the extracellular fluid. So this gives us big picture, right, where the water that's in our bodies goes. But it's interesting to ask the question, so, what happens, right, if you start to lose water, and lose water more so than the rate of exchange that's normal? So if you're at 0%, you have normal heat regulation. If you're at 1% loss of body mass in terms of water, your thirst gets stimulated, and you start to change the way that you can regulate heat. And if you go up to, say, for example, 4% of percent loss by body mass in terms of water, your exercise performance, your ability to do work, gets cut by about 20 to 30%. And if you step that all the way up to 7%, collapse is likely unless whatever the output that causes that loss is stopped. And so it's useful, I think, for us to have this moment where we think about, okay, so if I'm taking in water and I'm losing water, and right, this water has a significant role, what is its role? And so for that, we're going to turn to these fluids again, our intracellular fluid, and then our two components of extracellular fluid, the interstitial fluid and our blood plasma. And we're going to look at the ions that are solvated in those fluids. So if you take a look at this graph, you're going to notice the total solute concentration on the y-axis. Notice the units for that are milliequivalents per liter. And on the bottom, on the x-axis, you're actually going to see a variety of different cations and anions. So if, for example, we take a look at sodium, sodium is present in a significant amount in both blood plasma, and our interstitial fluid. So you have a lot of sodium in your extracellular fluid, where by comparison, you have relatively little sodium in your intracellular fluid. However, if we contrast that with potassium, we have a whole lot of potassium, right, in the intracellular fluid, but very little of that potassium in the extracellular fluid. You can go down and take a look at each of these cations and anions, right? And you can start to think about, well, why might it be necessary that you have a significant amount in your intracellular versus maybe not so much in your extracellular? And when you have amounts that are relatively minimal, what else does that tell you? And so part of the role of water is to be able to solubilize and to transport, to diffuse these ions. Now, the other role that we need to think about in terms of water, in addition to signaling and the transport of these components, is the role that water plays in terms of hydrogen bonding. So these are forces that shape molecules. If we think about the hydrogen bond itself, there's a couple of pieces that we notice right away. It's sp3 hybridized, so it's got 2 lone pairs and 2 bonds, so it's tetrahedral, but it's bent because of the role of that 2 lone pair. So we can see this angle of 104.5 between the 2 bonds. We also can see that there's a partial positive charge on our hydrogens and partial negative charge on the oxygen. And it's really that partial negative charge on the oxygen that's attracted to another molecule and its partially positively charged hydrogen. This quote, I believe that as the methods of structural chemistry are further applied to physiological problems, it will be found that the significance of the hydrogen bond for physiology is greater than that of any other single structural feature. So this was Linus Pauling in 1939, and he was really at that time hypothesizing what the role of hydrogen bonds were. But it's useful, I think, to think about how he really had this foreknowledge or foreshadowing of the role of hydrogen bonds in proteins, in nucleic acids, in a variety of structures that we find in living organisms. Now, if we think about non-covalent interactions, we have a couple of choices that we can explore. One is the charge-charge or charge-dipole interaction. The other is a dipole-dipole interaction. But we also have ionic interactions. And so what you can actually see here is the role of water in solvating ions. So if I had a cube of table salt and I were to drop that into water, eventually I would start to see that salt dissolve. What would it mean for it to dissolve? What would mean that the hydrogens on water molecules surround the negative chloride ion, and the oxygens on water molecules surround the positively charged sodium. And that's how I would solubilize a salt. If we go back to some of these other non-covalent interactions, we can see a couple of features. So non-covalent interactions do not involve sharing a pair of electrons. That's a fundamental definition. We can distinguish between them based on what the interaction, though, looks like. So we just talked about an ionic interaction. That's where I have 2 permanently charged species, or between an ion and a permanent dipole. And usually it's a negative and a positive charge that have that interaction. It's possible for there to be repulsion, the result of 2 charges that are the same. And then I have dipole interactions. So this is where I have uncharged polar molecules. And I can have a couple of different kinds of that. So, right, if I think about the high dielectric constant, right, I have this charge-charge interaction. And if you think about the impact that that's going to have, right, ionic interactions are going to be relatively short range, so 10 to 40 nanometers in aqueous solvent. That's going to be really important when I think about intermolecular interactions. The dipole-dipole interactions, right, are what really allow for the solvation of polar molecules. And I can think of hydrogen bonds within the context of dipole-dipole interactions. It's a special dipole-dipole, where I have a highly polar NH or OH. And then I have another hydrogen that can interact with that electronegative atom. So if you think about this attractive, so an induced dipole interaction that occurs over a relatively short range, as opposed to, say, for example, the van der Waals interactions, which are incredibly weak, and require incredibly short distances to have effect. So these can be attractive or repulsive, but really only r to the -6, r to the -12th as a distance. And then we're going to look at the hydrophobic effect. And this is a phenomenon that really has to do with the way that water molecules order around nonpolar substances. So if I take a look at examples of these non-covalent interactions, I'm probably going to want to have at least a reference point as an example for each of these going forward. So if I take a look at hydrogen acceptor and hydrogen donor, I can see that that can actually come from a variety of different functional groups. As long as I have an electronegative oxygen or nitrogen compared to, right, a lower electronegativity hydrogen. And then you can actually see where these occur. So whether that's between the hydroxyl group of an alcohol and water or between the carbonyl group of a ketone and water, there's a variety of examples that we can see for hydrogen bonds. It's probably worth having a conversation where we talk about why it is that distance impacts the type of bonds that we have. So if we think about forces, right, we have both attractive and repulsive forces. And you kind of have three pieces that I want you to think about here. The first is you have Coulomb's law, which defines force with respect to charges and the distance between those charges. You also then have this repulsive potential and an attractive potential. And so this really specifies across a significantly large distance, you have relatively minimal attraction. Across relatively close distances, you have pretty significant repulsion. And so really what this shows is that there's this sweet spot, what we think of as the binding energy. And so it's this ideal position where at this point, I am minimizing my repulsive potential and maximizing my attractive potential. And this is the ideal distance, r, of my bond. So if I'm going to have electrostatic force versus a separation distance for oppositely charged particles, right, I'm going to have this well. And really it's this position, right, where I'm looking at my ideal, right, bond distance. And so this is the best position to maximize my attraction and to minimize my repulsion. Now, it's worth having a conversation about how when we're thinking about intermolecular and intramolecular forces, we need to have an understanding of the relative strength of those forces. So intermolecular forces are forces that are between molecules. Intramolecular forces are forces that are within a molecule. And so these are going to vary in terms of strength, and you can actually see the different types of forces that we've talked about so far here. And notice the units that are provided here are in kilojoules per mole of interaction, so we're really talking about how much energy each of these bonds have relative to each other. And you can actually look at then over a distance, right? What is the relative strength of these bonds? Are there other factors that come into play, say for example charge, like Coulomb's law? And then what's the magnitude, right? How strong are these intermolecular forces? And then, is there anything that we need to take into consideration, right? So covalent bonding is highly directional, right? Induction is always attractive, but it's non-additive. This is kind of a great summary slide to give you a picture of what these forces look like. Last thing we're going to really talk about for this part is water, when it surrounds a polar substance, forms this beautiful, exquisite, tightly bonded hydrogen series, right? So we have lots of hydrogen bonds all over the place if I have a polar molecule. And so there's going to be this net decrease in entropy. However, if I look at something that's nonpolar, what I'm actually going to see is that there's this very specific clustering that occurs. So my hydrophobic, the non-polar part of my molecule is going to tend to cluster together. And then my water molecules are going to order themselves around. And so my entropy in this case is going to be maximized. Right? It's relative to my surface to volume ratios. But this idea that the role of water with respect to non-polar molecules can be just as significant as water with respect to polar molecules. Its response is different. The way that it orders itself around that molecule is different. But it has a significant role with respect to entropy. So if I think about the dispersion of lipids in water, right, this is why when I mix oil and water, there's an obvious separation, because water becomes highly ordered at the edges. And so my entropy increases, and then I have fewer water molecules that are ordered. Now, most biomolecules are actually some combination of hydrophilic and hydrophobic. And if I think about the two major determinants of biomolecular structure, well, it will come as no surprise that hydrogen bonding and the hydrophobic effect are pretty significant players. So if I think about membranes, for example, it's the hydrophobic effect that creates the lipid bilayer. If I think about proteins, it's the hydrophobic effect that drives the creation of that protein core, where I segregate the hydrophobic components of my side chains, and I have internal H bonds. In DNA, it's the hydrophobic effect that drives the formation of the double helix, and then I actually have aromatic bases that are in the interior and hydrogen bonded. And then I have this backbone that's exposed to water. And so if you think about just these molecules from a structural standpoint, right, I can think about how for carbohydrates, hydrogen bonds are major, but the hydrophobic effect is relatively minor. In a lipid, it's the reverse. Hydrogen bonds are relatively minor, and the hydrophobic effect is fairly major. In a protein, actually both are significant, and in a nucleic acid, both are significant. And so the last thing that's worth talking about here as we're kind of moving forward is this understanding that when we think about water, right, there's the actual properties of water in terms of its hydrogen bonding or the hydrophobic effect, but then there are also what we think of as colligative properties. So these are when solutes are dissolved in water and they change the properties of a solution. So you can think about things like freezing point or boiling point or vapor pressure or osmotic pressure that changes. And so that's really the direction that we're going next. We're going to take a look at how those colligative properties also influence the behavior of water. Thanks.